I'm on A. I'm going to define independence between random variables, say X and Y. Okay, independence. Definition of independence is a little what sophisticated or conceptual, but you keep in mind the word independence, okay, in your mind. Let's go. What the independence between X and Y? Okay, here there is a joint probability distribution function fxy for random variables x and y, right? The variables can either be independent or have a relationship. Firstly, it is essential to clearly understand the definition of independence. What is independence in statistics? As this concept is very important in statistics, it is important to understand independence in statistics. Chapter 1, we discussed idea of independence in relation to sample values. I told you sample values are independent each other. Otherwise, we got big trouble. And defined degrees of freedom. What is degrees of freedom? Number of independent items is degrees of freedom. While sample theory will be covered further, I think next chapter, chapter 3, it should be noted that statistical theory could not have advanced without the assumption of independence. So it is a very important base or assumption, okay, in statistics, independence. Definition. It is what? A little conceptual thing, abstract thing. If the joint probability fxy of xy is equal to the product of marginal probability distribution f of x and marginal probability distribution of y, f of y, then x and y are independent. The converse is also true. Say joint probability of x and y is product of f of x and f of y, marginal probability. Then we say x and y are independent. X and y are independent. F of xy equal to f of x times f of y. Okay? It is, isn't it what? Conceptual thing? Isn't it abstract thing? When tossing a coin twice, let the random variable be defined as x equal to number of heads in the first toss and y equal to number of heads in the second toss. Then x and y are independent. Conceptually, you know x and y are independent. But in statistics, how to define independence of x and y like this. Okay, this one is x, this one is y. X takes 0, 1, y takes 0, 1. The probability, what? Joint probability. Each cell, each case, 1/4, 1/4, 1/4, 1/4, right? What is f of x? 1/2. 1/2. Marginal probability of x. Marginal probability of y, also 1/2, 1/2. So each cell is the product of its marginal probabilities. Here, 1/2 times 1/2 is 1/4, right? For each one. So theoretically, we say x and y are independent. When tossing a coin and the die, x is number of heads when the coin is tossed. Y, number of that appears when the die is rolled. Okay. See here x. This one is y. Then x and y are independent. We can imagine, in that case, x and y are imagined. But theoretically, in statistics, each cell, as before, each cell has probability 1/12, 1/12, 12 cells. And marginal probability of x is 1/2, here 1/2, here 1/6, 1/6, up to here 1/6. So same as previous example, in this case also, each cell is the product of marginal probability, x and y. This is a simple example, and but it is important concept. Okay, x and y are important independent. Then it's going to be f of x times f of y. Okay, let's see. Next thing is correlation. Correlation coefficient. Correlation coefficient is indicator. I think you have heard this word, correlation coefficient, that represents the relationship between random variable x and y. Relationship. Okay, the value of correlation coefficient ranges from -1 to +1. I think it is like common sense, but it can be proved. Okay, but not here. Correlation coefficient of +1 indicates that as the value of x increases, the value of y also necessarily increases. Where there is a joint probability distribution function for two random variables f and y, there is an indicator that represents the relationship between x and y, which is called covariance. Okay, you have to understand covariance first in order to get correlation coefficient. Covariance is calculated as follows: x and y. This is covariance of x and y. It is expectation of x what deviation times y deviation. Deviation, x deviation, y deviation, the product terms, all product terms, and you get expectation, then it is defined as covariance. So how to get this one is for discrete case xi minus mu x deviation, yj minus mu y, its deviation, product, and times its probability, f of xi and yj, and the sum for x and y. Okay, I from 1 to p, j from 1 to q, something like that. That is covariance. But covariance is the product of the measurement unit of x and y. So, for example, x is measured in centimeter and y is measured in kilogram. Then the covariance has an abstract unit of centimeter times kilogram. Have you ever seen this kind of a unit? No, we cannot figure it out, making it difficult to interpret the magnitude of covariance. Even the same value, okay, same data, if you use the data, input data is gram, not kilogram, then it's going to be centimeter times gram. For same data, the magnitude will change by 1,000 times. Anyway, therefore, correlation coefficient removes the unit of covariance, uh, unit of a centimeter and kilogram. Correlation coefficient being discussed here, like this, is known as Pearson's correlation coefficient. Pearson's correlation coefficient, which is valid when x and y have a linear relationship. A linear relationship is like this. Okay, x increase, then y necessarily increase. Not necessarily. It is kind of okay, increasing this way. This is a linear relationship, x and y. Definition of correlation coefficient is correlation x and y. Oh, this is rho, R-H-O. It is also Greek letter. Statistician used to use this kind of a notation, rho, for correlation coefficient. So it's nothing but covariance divided by standard deviation of x and standard deviation of y. This is, say, for example, centimeter times kilogram, okay? And what is this? This standard deviation has what unit? Centimeter. And this one will be have unit kilogram. So the unit cancel out. So correlation coefficient has no unit. It lies from -1 to +1. This is a definition of correlation coefficient. You understand that? Okay, sometimes there are many chances to use correlation coefficient to represent your result. Okay, so at this time, you better understand what correlation coefficient. Okay, I will take one simple example in order to calculate how to calculate correlation coefficient. Okay, okay, that's it today. Thank you. Bye.